Now that we have seen the basics of how a program can be written, at least one possible environment that we can use in order to write a program and then compile it and run it, in particular using the Replit interface, we are going to dig a little deeper into what a program looks like, right? We saw a very simple example of a program in Hello World. We are going to now look at a slightly more complex example and go into that in a little bit more detail. Right? Programs written in C typically have many different components, right? Structural components that you need to be aware of. And when you look at a program written by someone else, the way to understand what is happening is to be aware of these components and recognize from that which are the parts that you need to focus on. Right? The first thing you will see in any program is that there will be some headers. Right? What are those headers? Those typically are sort of extra information at the front of a program, right, which tell you what are some of the other functionality that the program might be using later on at some point, and because it may need to make use of them, they are being sort of pulled into the program, so to say, right at the beginning. Okay. After that, there will be a number of function definitions, right, the functions that are used in order to actually run the core, the computation associated with the program. A very important part of the whole process of writing a program is also documenting what the program is supposed to be about. Right? So, writing comments is something that is there in every programming language, right? And it is essential in order to make your program in such a way that it can be later on understood by someone else, and that someone else might be a future version of you. Right? It is very common to write a program and then look at it 6 months later and not have any idea of why you wrote a program the way you did, right, unless you have hopefully documented it well to start with. We will also look at other components of the program, which are primarily statements and expressions, variables, how they are declared, and so on. And all of these, like I said, are the structural components of a program. Finally, there is one very important part, right, which is actually not a sort of mandatory part of the program, which is related to style, right. It is more about the aesthetics, about the looks of the program, if you will, right. But even though it sounds as though, okay, that's obviously less important than the other parts, if you want to write a program that is actually understandable and usable, this matters a lot. Okay. So, I will be discussing that a little bit, and it will be expected that any programs that you write as part of the assignments and so on do follow certain kinds of style guidelines, and they should be readable and they should be sort of well structured. So, what we will be doing is going deeper into this piece of sample code, right. Before I actually start analyzing the code itself, I am going to switch over to Replit and actually show you the full code and run it and show you what the output is going to look like. So, this is a Replit that I have created, which is called add numbers, right, and as you might imagine, what the add numbers Replit does is that it has some code out here, right, which looks long, right, it is already gone longer than one page, okay, and that does something. What is that something? We are going to sort of figure out, and we are going to look at what exactly it does, and then we are going to get back and analyze the code in a little bit more detail to understand what are the structural components that are involved out here. Okay. So, in order to understand a C program, rather than starting at the top and sort of making your way down, the usual better way of understanding it is just jump straight to the main function, right, because after all this is the entry point. Everything else above or below the main function is secondary. It may or may not be called by something that is happening in the main function, but you can be sure that if at all you execute this program or you run it, this function is going to run for sure, right. And as you can see, Replit also tells you that. It says that this is the top level function that is automatically called. It also uses the word the C runtime handles this, right. So, what is this runtime? That is basically the operating system, right, or rather it is a component that is provided to you by the operating system. What happens with the runtime is that there is some extra machine code that gets combined along with the code that you have written in order to create the executable program, right. Like I told you, when the operating system actually wants to run your program, it needs to know where exactly to jump in or where to set the program counter to start things off. The runtime makes sure that the main function is the entry point that is provided for your program, right. So in order to understand what a program does, like I said, jump straight to main, read through it and try and figure out what's happening out there. Now if you look at this, you will find that there are basically 3 lines of code in main, right. I mean, the blank lines don't really count as code, they exist but they are not required for the program. What is required is this first line out here, which says int a of the square brackets, we usually pronounce it as a of n, right. And what this is saying is that this is actually declaring something called an array. We have not yet discussed arrays, of course. So right now all that you need to think about is that this a is going to be some block of memory which contains a list of numbers, okay. Printf we are already familiar with because we know that, for example, it could print a message like hello world. But over here you find that it's actually printing something a bit more complicated. It prints out a string saying sum equals and so on, but then there's suddenly this %d, one an unexpected symbol, right. It's not really what you expect to see in the middle of the output of a program. It turns out that what printf does is, whenever it sees these percent things, it then sees what is there after that string out there, evaluates it as a number. In this case, d means it's expecting a decimal number, evaluates all of this as a number and puts that value in there. So it should run this function, get a number as the result, put that number over here, and the message that I should get out should hopefully be sum is equal to whatever that number is, okay. Once again, what's a function? Like I said, that's also something that we will be getting to later, but at a very high intuitive level, it's sort of easy to understand what a function is, right. It takes certain inputs. In this case, it takes a list of numbers a. It also takes this n, which is a single number that I have defined up here, right, to be 10, right. So it takes in these two values or these two sets of values, because a is a list of, it's a set of memory locations, right, containing numbers in themselves, and add nums is going to add them up and give me back a result, okay. And what we have over here is the actual definition of add nums itself, right. We will get to that later, but the important point is now you can intuitively understand what this program is expected to do, right. It should call this function add nums, put that into the string out here and print it onto the screen. Let's see if it does that. When I run this, right, I find that I switch back to the console on the right over here. Once again the make -s compiles the program, right. Please keep in mind that make is not fundamentally part of the C programming language, right. It's just a helper, it's a tool that is commonly used in order to take care of compilation, and Replit has chosen to use this particular approach for compiling things, right. You could compile programs in a different way as well. We are not going to get into that right now. We may look at it at some other point when we actually look into how programs are going to be constructed, right? Or when you look into the internals of the program. But what has happened over here is it ran the make -s in order to actually do the compilation. It ran the program ./main, and as expected, right, the sum equals was replaced, was followed by a number, and this number 42 happens to be the sum of these 10 values that we have out here. Okay. So effectively what has happened, this program in other words has taken a list of 10 values which are stored somewhere in memory and has somehow added them all together and given me a result. Okay. Now let's look a little bit closer at the structure of the program, meaning that what are all the other components that we had out here. So this is a snippet of the sample code that we looked at, right, as part of the add nums add numbers Replit, and there are a number of different parts of the code that I want to draw attention to. This first part out here that you can see is these two lines, line number 1 and 2, right. The first one basically says hash. This symbol out here is usually pronounced as hash, right. You might in American terminology, I think they call it pound sometimes, right. The general the convention we follow is we just call it hash. So hash include and stdio.h, right. These, the less than, greater than symbols are usually called angle brackets in this case. They are not explicitly called less than, greater than. So the angle brackets are, there are many different kinds of brackets that end up being used in programs, right. There are the regular parentheses that you might be used to out here. There are what we call the curly braces or curly brackets. There are these square brackets that you find out here, and in this case there are also angle brackets. Okay. So angle brackets are used in relatively few places. This is one of them, but hash include stdio.h is what's called a header file, right. And what it does in this case is it tells the compiler that I want to make use of certain functions that are present in a standard input output library. That is what stdio stands for, right. And I will be making use of certain functions that are present over there. The function is essentially the function printf, okay. But in order to use printf, I need to have that stdio.h declared, right. Unless I have this header, I can't make use of another function. So we can see that C uses those header declarations in order to tell the compiler a little bit about what kind of functions I am likely to be calling later. Okay. The next line, hash define n10, is interesting. It sort of looks like I'm taking the value 10 and I'm giving it a name, right. Effectively that's what I'm doing. I'm using the name capital N in order to refer to the value 10, okay. Or another way of thinking about it is, from now onwards, any time that I use the symbol capital N by itself, right, not as part of another word, what I mean is that I want the number 10 to be put in there, right. We will see later that yet another way of doing something like this is to actually use variables, but please be very clear, something which is hash defined is not a variable, right. In particular, it cannot be changed later on in the program. More importantly, these hash defines are something which is not really part of the C compiler at all. It is something else called a preprocessor that handles these defines, right. So it actually happens in one step before the actual compilation process. There are a number of useful ways in which you can make use of this preprocessor, right, to define something called macros, right, which we will be getting to later, but for the time being all that we are doing is defining it as a constant. What matters in this case is anytime I use the capital letter N somewhere else in my code just by itself as a standalone value, what I actually mean is that's supposed to be replaced by the number 10. Okay. Okay. The next thing that you can see out here is there is a function definition, right. So I have this add nums out here, right, which is a function. And this particular part of it, right, where I have declared the function this way, you might find in certain other places, especially inside header files, that this definition out here, right, is actually going to be just placed by itself on a line, right, without any actual functionality behind it, right. That's sometimes also called a prototype or a function declaration, right. We will see more of those when we start writing larger programs. For the time being, what matters is that this is where I am actually creating a function, and I need to start that. The first part of defining a function is to actually tell what the function is like, meaning that what does it take as inputs, what is the name of the function, and what does it generate as an output. Okay. The next thing that you would have noticed, and of course, like I said, everything else between these curly brackets out here is actually what's called the function body, right, which actually tells us what the function is doing. The next thing that I want to draw attention to over here is that you will notice that there are these things that have been slightly grayed out by the editor, right. Once again, all these colors are not part of the language, they have been introduced by the editor. You probably can customize these colors to a large extent, and you could choose other colors that maybe you like better, right. They are usually called different themes or different coloring patterns, different approaches that are used in order to highlight the different parts of the program. The purpose is of course simple, it's basically to make it easier to understand or visually examine and understand what is happening in the different parts of the program, right. But it's not a core part of the language itself. But in this case, what we have is this first part out here, lines 4 to 8, right. You can see it starts off with the symbol slash, right. This one here is what we usually call the forward slash or just slash, followed by the asterisk or the star symbol, right. In this case I have put 2 stars, right. So slash star star, not necessary, just a single star also could have done, right. What matters is that the moment I give slash followed by star, that's indicative that I am beginning a comment, right, in the C programming language. Everything that follows after that, these stars are not really necessary, I am just putting them there for aesthetics because it sort of helps to line up all the text that is present over here, right. I do not need it over there. Some people also tend to put a whole line of stars out here and another line of stars out here. There are many different ways of handling the commenting and the documentation part. Once again, a large part of it comes down to personal preference, right. As long as you have good documentation, the exact style of how you present it is secondary. What matters in this case is that the document that I have over here is actually telling me a little bit about what the function is, right. It says it's a function that adds values that are stored in an array, and it returns a single value which is the sum, okay. Now it's up to you to sort of decide, is this a useful piece of documentation or not, right. To some extent yes, because at least in my opinion it's not a bad piece of documentation. It tells you clearly what the function is doing. If it had instead said something like it takes int star a as input and int numvals as output and gives an int as an int numvals as input and gives an int as output, that's useless documentation because it's not really telling me what a, numvals and so on are. But this documentation is actually telling me that it adds values that are stored in an array. So I need to look for an array. Of course I have something over here, we will get to this much later when we talk about how arrays are passed into functions and so on. But it's telling me a little bit more about the logic, about why I have written the program the way I have done so, right. There is another comment that I have over here where I say I am creating a variable to use as a counter. Okay. There is yet another one which says another variable to hold the sum that is being computed, right. And finally one more comment out here saying, okay, this what follows out here is a loop. I am going to repeat that block many times. This last one out here in this particular case is not a particularly useful comment because the moment you know anything about the C programming language, you realize that for is a loop construct, right. So is this particular comment useful? Not really, right. All that it's saying is, yeah, that for what follows is a loop. I could have inferred that just by looking at this line itself, right. Instead, if I had something that said loop over all the list of values and add them, that is probably a slightly more useful comment, okay. So clearly, as you might have figured out by now, the quality of comments is first of all subjective, right. Each person might have a different idea of what is a good comment, and the number of comments that you need to use is also something subjective. But what you need to keep in mind is that having good comments, useful comments, is critical to your being able to understand what the program is about at a later point in time. Apart from that, we have what are called statements, right. So you will see that there is, for example, this, it's a declaration, right, which basically says int I, right, and all that this says is I am creating a variable named I which is of type integer, and you will see that I have just sort of put that by itself on a line, and followed it with a semicolon, right. Now the semicolon is something that you will see a lot of while writing C programs, and the reason is that C uses semicolons in order to separate out the different statements that are present in your program, right. Remember that we said that C was an imperative programming language. What that means is, in a C program you give a set of commands to the computer that it needs to follow. Effectively, statements are like those commands, right. Each of those statements is some particular sort of instruction to a computer in order to do something. Now you might wonder, hey, what exactly does something like int I do? How is that an instruction to a computer? In this case, what it's saying is it's basically instructing the compiler to set apart space where that variable can be stored, right. Another one is sum equal to 0, right. So this is sort of easier to understand. It's sort of saying that I have a value, a variable, and I want to assign the value 0 into it. Once again, just a statement followed by a semicolon, okay. Return sum is yet another example of a statement. Each of these is sort of a standalone statement. For that matter, sum equal to sum plus a of I is also a statement, right. But in this particular case, the reason why I am looking at it separately is that this part of it, the right hand side of that equals sign, the sum plus a of I, is what I call an expression, right. Expressions have values, sort of evaluate to values in themselves, right. So unlike a statement which is sort of giving an instruction to a computer, an expression is something that gets evaluated and is used as part of a statement probably, right. Now one thing to keep in mind is, yes, I have said this about statements and about expressions. These are not hard and fast or set in stone definitions. You do not need to, in particular what you will find is that in a language like C, it is quite possible that certain expressions can directly be used as standalone statements where they do something on their own, and certain statements may in turn have a return value of their own, right. It is possible to have something which is just used as a statement which causes something to happen, but which also returns a value of its own that could potentially be used in other places, right. So the distinction between statements and expressions, it is helpful in terms of understanding the structure of the program, but it can also be quite fluid in terms of what you would consider a statement versus what you would consider an expression, especially in a language like C. There are other languages where this distinction is a lot more rigid. So like I said, statements may sometimes return values. Does that mean that they can be considered as expressions? It depends on what you are going to use those values for. And similarly, an expression can be invoked as a piece of standalone code. Does that make it a statement? Since you have not taken the value of the expression and assigned it or done something else with it, does it mean that it's now a statement and not an expression, right? Like I said, these things are useful in terms of constructing the grammar of the language, but are not necessary in order to understand how the language itself works. Finally, we will see that there are a number of different names that we have over here. For example, there is this int I, there is int sum, right. All of these are essentially declaring certain storage locations, certain values. We will get to these in a little bit more detail later, right. These are what are called variables. This looks very similar to variables. The only difference is it is explicitly sort of being indicated as part of this function definition out here. So we call them parameters rather than variables, because A, although it can be used inside this function, is coming from somewhere else. It's not, this by itself is not the declaration of the variable A. And finally, we have yet another sort of set of symbols that are there inside this program. For example, you will see that sum equals, sum plus, and I plus plus, right. All of these are what are called operators. Once again, we will look into what exactly operators are in a little bit more detail later. So to quickly sort of summarize what we have seen so far, a C program follows a certain grammar, right. There are rules to what is allowed to come where in the different parts of the program, right. And the syntax, the word syntax is used to refer to that grammar, and it is typically the first step that is checked by the compiler, right. if a program fails a syntax check, it's usually fairly easy to figure out where it went wrong and usually also to fix it, right. So the first thing you need, of course, is that your program should pass all the syntax checks. It should be able to compile in the first place. If your program does not even compile, there is no hope of going beyond that, right. But usually the compiler will help you a lot in terms of sort of figuring out where the syntax errors are and telling you about them. Having said that, compilers like C compilers are notorious for not giving really useful error messages, right. There will be some places where, of course, it will give you a very obvious and simple message saying missing semicolon or something else of that sort, and it will be very easy for you to go there and fix it. But there can be other scenarios where it gives you a totally strange looking error message which is actually related to something, a problem that happened many lines away from where it's reporting the error, right. And part of that is because the syntax of C, the definition of the C grammar, is a little bit more complicated than it really, strictly speaking, it's arguable, right, whether it really needed to be that complex or not. But compilers struggle with that sometimes, struggle with giving you good enough error messages that you can use in order to find out where exactly the problem is. Now, the semantics of the program is something totally different. This refers to what the meaning of the program is, the actual logic that you are trying to implement, right. What happens, in other words, is once you have compiled your program, you are now ready to run it, right, and that is where the semantics comes in. That's where the computer actually needs to execute your instructions and perform the operations, execute the meaning of what it is that you are trying to do, right, and get the whole thing sort of going with that. The semantic errors or logical errors with your program are typically harder to debug. They are where you actually usually struggle in terms of finding out what has gone wrong and why is it that the program is not giving you the exact result that you expected from it. Finally, a word about the style, right. As I mentioned at some point, this refers to aesthetics, how good something looks. It's difficult to quantify, right. You can't really look at a piece of code and say, okay, this is 95 out of 100, although some people try and do that, right. The point is, it is subjective, but it greatly impacts how readable and reusable your code is, right. There is also this concept of indentation, right, which I will talk about in a moment. The way to think about it is poetry, for example, right. You would have seen poems in many languages, possibly, well, human languages, right, and you know that each line of the poem has a certain point at which it stops and then goes over to the next line. And the reason is, of course, the end of the line has to rhyme usually with something that is coming up on the next line. So poems have a very specific structure, whereas prose is just text. You can reformat it, you can take a word from one line, move it to another line, move the thing around, and it doesn't change its meaning, right. You need to think about a program as something closer to poetry than to prose, right. Where you put the different parts of your program and how you structure it can make a big difference to how readable and how understandable it is. Similarly, there are many things that come up in terms of conventions about readability. How do you name the different variables, functions and so on that you are going to use inside your program, and what kind of documentation do you use, right. And the other thing that comes up in terms of style is the structure of the program itself, right. What I mean by structure is, how do I define where the function boundaries are, what is going to be encapsulated inside one function, which function calls other functions and so on, okay. Now, to briefly discuss a little bit more about the aesthetics part and the indentation, I just want to take an example of the same code in Replit and show you what kind of a difference it can make. So the first thing that we can see in Replit is, if you look at the way that I have written this code, right, I have a little bit about the headers, then I leave a blank line, then I have the comment corresponding to the function immediately followed by the function itself, right. And even within the function you might notice a few things. For example, this left open curly brackets lines up vertically with the right curly bracket, right. Everything else which is inside the function is indented. Indented meaning it is shifted a little to the right. In this case it is shifted by 2 spaces, right. There are other editors and other choices where you might shift it by a tab instead, right. This by itself is the source of many arguments on the internet, right. We are pretty much going to go with whatever is the default that Replit uses. It's a fairly decent indentation style, so pick one and go with it for the most part, right. It's impossible to find one particular indentation that satisfies everybody. So for the most part we will be going with what is used over here. You will also notice that, for example, I have this structure out here called the for loop, right, and you will notice that everything, or in this case there is only one line out here, but what is inside the for loop is once again indented even further, right, from what was there at the beginning of the for loop. Similarly, this curly bracket matches with this curly bracket, but I have not lined up the two curly brackets. Instead I have lined up the beginning of the for loop with the curly bracket that closes it, right. These are once again choices, right. Everything else you will see essentially starts on the same line, the same column number, right, which just sort of aligns things neatly. It is just making sure that everything is in a straight line and it's easy to see and read, right. As an example of what not to do, or rather how to sort of mess up the code, let's take a brief look at another example of the code. So what I have over here is exactly the same program, the add numbers program, but now I have intentionally gone in and tried to mess things up a little bit, right. So not too much really, right. One of the things I did is I took this the documentation and moved things around so that now the starting of the documentation comes on the first line, there is a star on the second line which is not really aligned with the star on the first line, the star on the third line is not aligned with any of the others. After that I have the declaration of this function, and the parameters that it uses are also split across multiple lines that are not lined up together. I have a curly brackets out here, and if you go down and look at it, then it actually is supposed to align with the curly bracket out here, right, but it doesn't. There is nothing aligning things properly out there. I have a for loop out here which then has some kind of curly brackets, some indentation which is all over the place, some unnecessary blank lines out here, right. It's exactly the same function as what was there before. I have not added or removed a single piece of code. All that I have done is moved things around, right. But you can sort of imagine that this is already harder to read than the previous version, right. For the most part Replit will take care of a lot of this for you, right. It will help you with aligning things. In fact, by default it also has a mechanism whereby the moment you save a particular file, it will automatically do some reformatting for you and move things around into the right places, right. Try and make use of those, but as far as possible try and also absorb the rules that are being used, so that even in case you do not have access to Replit, you still follow fairly reasonable conventions for how you go about formatting and indenting code. The other related thing is, for example, the names of functions. Add nums is sufficiently descriptive, right. It sort of tells you what it is and what it expects as input. But at the same time it's not terribly long, okay. There are arguments about this as well. There are fairly reasonable arguments to say that the length of the function name doesn't matter, because after all with a modern IDE, the editor will sort of help you to fill out the names properly, so you don't need to type everything out on your own, right. So why not just use longer names that are more descriptive and easier to understand. At the same time, long names also mean that the entire text of the program spills over multiple lines. That can have an impact on readability as well, right. Similarly with variables, I have one variable called numvals, which it's reasonable to assume is the number of values to be added, another variable called sum, which is the actual running sum which I am computing. But then again I have a variable called I, right, and this is once again a matter of convention and preference, but I prefer to use simple names like I or j in order to implement counters, because they are very common, right, and having a long name like this is a counter to add the values together is just not helpful. Okay. So how you go about doing indentation, how you go about naming functions, naming parameters, naming variables and so on can have a significant impact on how your program is read and understood, and on the overall structure, how you go about understanding your program and documenting it for others to read and understand.